Good morning, all of you. Today I am going to make an audio recording for visual impaired students of Organic Chemistry book of Dr. J. M. Sehgal, modern book. Name of the chapter is Structure and Bonding. 1.1 Introduction to Organic Chemistry. The term organic compounds was originally applied to compounds such as sugar, alcohol, oils, and fats, which are derived from vegetables or animal sources, that is, from living organisms. This was done in order to differentiate such compounds from inorganic substances such as common salt, sulfur, and metals which are obtained from mineral resources. The study of organic compounds gradually began to develop as a separate branch of chemistry which came to known as organic chemistry. The chemistry of inorganic compounds was therefore distinguished by calling them inorganic chemistry. Vital force theory. In the early days of the growth of organic chemistry, it was considered impossible to prepare organic compounds in the laboratory. Berzelius suggested that organic compounds could be produced only under the influence of some mysterious forces existing in living organisms. This force was called vital force, from the Latin word vita, life, and the theory of Berzelius came to known as vital force theory. However, in 1828, Wohler synthesized urea, an organic compound present in the urine of animals, from ammonium cyanate, an inorganic compound obtained from ammonium sulfate and potassium cyanate. NH4 twice SO4 plus 2 KCNO gives ammonium cyanate plus K2SO4. Ammonium cyanate gives urea. This synthesis of an organic compounds in the laboratory shook the faith in the vital force theory. In 1945, Kolbe synthesized acetic acid from inorganic sources, and the laboratory synthesis of many other organic compounds soon followed. Consequently, the idea of vital force was completely discarded by 1850 and is firmly established that formation of organic compounds does not depend upon any special force. Thereafter, the number of synthetic organic compounds began to rise at an ever growing rate. Modern definition of organic chemistry. With the rejection of vital force theory, the major differences between organic and inorganic compounds disappeared and the term lost their original significance. But organic chemistry continued to be treated as a separate branch of chemistry, although it was given a new definition. Organic chemistry is now defined as the chemistry of the compounds which contain carbon as an essential constituent. A few compounds of carbon, such as carbon monoxide, carbon dioxide, and carbonates, organic by above definition, are however studied in organic chemistry, which deals the study of any other elements and their compounds. The simplest organic compounds are hydrocarbons, which are made up of carbon and hydrogen. All other organic compounds can be considered to have been derived from hydrocarbons by the replacement of one or more hydrogen atoms by other atoms or groups. Therefore, organic chemistry can also be defined as the chemistry of hydrocarbons and their derivatives. Theoretical aspect of organic chemistry. There has been a strong growth of theoretical understanding in the field of organic chemistry in the last few decades. This has been very helpful in interpreting the details such as mechanisms, rate of occurrence, and the effect of temperature, concentration, etc. of the large variety of chemical reaction encountered in organic chemistry. In order to appreciate the theoretical aspects of the subject, the students must have a clear understanding of certain fundamental concepts. We are introducing a few relatively simple concepts in this chapter. 1.2 Nature of bonding in organic compounds. The carbon atom's atomic number 6, which is the common feature of all organic compounds, has the electronic configuration 1s2, 2s2, 2px1, 2py1, and 2pz0. Thus, it has got 4 electrons in the valence shell. In order to acquire a stable noble gas configuration, in its compounds, carbon should either lose or gain 4 electrons or alternately share 4 electrons. But the loss or gain of 4 electrons leading to the formation of C plus 4 or C minus 4 ions would require the supply of a very large amount of energy, which is not possible during ordinary chemical processes. This implies the carbon cannot form ionic bond in its compounds and must form only covalent bonds. In other words, covalent bond is the bond of main importance in organic chemistry. According to orbital concepts, a covalent bond is formed when a half-filled valence orbitals of an atom overlap a half-filled valence orbitals having an opposite spinning electron of another atom. Now a carbon atom has got only two half-filled valence orbitals, that is 2px1 and 2py1, and therefore it may be accepted to form only two covalent bonds. But in actual practice, carbon is known to have a covalency of 4 in its compounds. To explain the tetra covalency of carbon, it has been postulated that at the time of bond formation, the two electrons in the 2s orbitals of carbons are unpaired and one of them is promoted to the empty 2p orbitals. This gives rise to electronic configuration 1s2, 2s1, 2px1, 2py1 and 2pz1 as shown below. 2p 2 electrons, 2p next 3 electrons, 2s 2 electrons, electron promotion 400 kilogram mole per second. 2s 1 electron, 1s 2 electrons, ground state of carbon, excited state of carbon 1s. In its new state called excited state, the carbon atom have 4 half-filled valency orbitals which would be available for the formation of covalent bonds. Thus carbon atoms exhibit a covalency of 4. It may be noted the formation of 4 bonds by carbon would result in greater lowering of energy and formation of more stable molecules than if carbon were to form only 2 bonds. This extra lowering of energy more than compensates the energy needed to promote an electron from 2s to 2p orbitals. This means that even though the promotion of electrons is by itself not favored energetically, since it takes place with the absorption of energy, it's ultimately lead to greater lowering of energy by enabling carbon to form 4 bonds in place of only 2 as illustrated ahead. Ground state 2 half-filled electrons plus 2H gives HCH. Ground state 2 half-filled orbitals in presence of absorption of carbon gives C. Excited state 4 half-filled electrons in presence of release of 4 into 418 energy of CH bonds gives CH4. Thus there is a net release of 836 energy in the formation of CH2, while there is a net release of 1272 energy in the formation of CH4. Bond energy. The process of bond formation is accompanied by release of energy, and the bonded state represented a state of lower energy that the individual atoms. It therefore follows that an equivalent amount of energy will have to be supplied to break the bond. The amount of energy required to break a bond and separate the bond atoms in the gaseous state is known as bond dissociation energy or simply bond energy. It is generally expressed in kg per mole. Thus, the hydrogen molecules have a bond dissociation energy of 433 kilojoule per mole. HH gas 1 mole plus 433 kilojoule bond dissociation energy gives H star 1 mole plus H star 1 mole. It may be mentioned that bond energy is also equal to the amount of energy released when 1 mole of hydrogen atoms combine with 1 mole of hydrogen atoms to form 1 mole of hydrogen molecules containing 1 mole of hydrogen bonds, as H1 mole plus H1 mole gives H1 mole plus 433 kilojoule. It is apparent that bond energy is a measure of the strength of a bond. Greater is the bond energy, stronger is the bond. Factors on which bond energy depends. First, size of bonded atoms. Bond energy is inversely proportional to the size of bonded atoms. The greater the size of the bonded atom, smaller is the bond energy. This is due in bigger atoms, the overlap of atomic orbitals is less efficient. Second, bond length. The smaller the bond length, higher is the bond energy. Smaller bond length means greater and stronger overlap of atomic orbitals, which result in a greater bond energy. Third, nature of rest of the molecules. The energy required to break a particular bond between two atoms has a specific value only for that bond and is generally termed as bond dissociation energy. But when a certain bond may be present in molecules of different substance, the actual value of bond dissociation energy of that bond will vary from one compound to the another. For instance, OH bond may be present in water as well as in methyl alcohol. The bond dissociation energy of OH bond in water is different than its energy in methyl alcohol. In a polyatomic molecule, even the energy required to break a particular kind of bond may have different values. For example, the 4CH bond in CH4 are equivalent, but the energy required to break the first bond CH4, that is CH3 plus H positive, is not the same as the energy required to break the second bond CH3 gives CH2 plus H positive, and so on. This difference in bond energies of even the same kind of bonds is due to the fact that the energy of a bond depends upon the nature of the rest of the molecules as well. Therefore, when giving the general values of bond dissociation energy of such bonds, only the average values are stated. The average value are generally referred to as bond energy rather than bond dissociation energy. Bond energies of some bonds are given in table 1.1. Table 1.1. Bond energies of some bonds. Bond energy. HH 433, HO 335, HCl 427, H double bond O 695, HBr 364, CF 448, HI 297, CCl 326, CH 414, CBr 285, CC 347, CI 213, C double bond C 607, OH 464, C triple bond C 803, and single bond H 389. The values of bond energy given in the above table for HH, HCl, HBr and HI are their actual bond energies actual bond dissociation energies, while the values given for other bond are the average bond energies. 1.4 Localized and delocalized chemical bonds. 1.4.1 Localized chemical bonds. When a covalent bond is formed by the overlap of two atomic orbitals, the orbitals that result are the properties of the molecules, not of the individual atoms. That is why the resultant orbitals are known as molecular orbitals. The electrons in these orbitals are shared between the atoms involved in bond energy formations. For example, let us consider the formation of an hydrogen molecules from two hydrogen atoms, each having 1s electrons with anti-parallel spin relatively to the other. When the 1s orbitals of the two atoms overlap, the two 1s electrons become paired and begin to occupy the same molecular orbitals. The probability of finding these electrons is greatest in the region between the two nuclei. It is due to the concentration of negatively charged electrons between the two positively charged nuclei that the two nuclei are bounded together. It may be pointed out that even though both the electrons are negatively charged, they tend to concentrate in the internuclear regions due to their anti-parallel spins. The net result is that electron density for the electrons involved in bond formation is greater in the region between the two nuclei. Therefore, the two paired electrons are said to occupy a localized molecular orbitals, and the bond formed is known as a localized bond. A localized bond may therefore be defined as the bond whose electrons are greatly concentrated in the region between the two nuclei only. A sigma bond between any two atoms, a pi bond between two atoms in a molecules having only one double bond, or the pi bond in a molecules having isolated double bonds are also localized bond. All bonds shown above include CH bonds are localized bonds. CH2 double bond CH2, CH2 double bond CH, single bond CH2, single bond CH, double bond CH2, localized pi and alpha pi bond, sigma and pi bonds. 1.4.2 Delocalized chemical bonds. To understand the concept of delocalized chemical bonds, let us consider the case of a molecule containing double bond and single bond in alternate positions. Double bonds which alternate with single bonds are said to be conjugate. For instance, 1,3-butadiene is a conjugate diene, while 1,4-pentadiene is a non-conjugate diene having isolated double bonds. CH2 double bond CH, single bond CH, double bond CH2, 1,3-butadiene conjugated alternating double and single bonds. CH2 double bond CH, single bond CH2, single bond CH, double bond CH2, 1,3-pentadiene non-conjugated non-altering or isolated double and single bonds. Let us now discuss the molecules of 1,3-butadiene as a typical case of the formation of delocalized chemical bonds. Each of the 4 carbon atoms of 1,3-butadiene is in a sp2 hybridized state, having 3 sp2 hybridized orbitals and 1 unhybridized p orbitals. The 3 sp2 orbitals of each carbons are used in the formation of sigma bonds with adjacent carbons and hydrogen atoms, and all these bonds are localized bonds. The unhybridized p orbitals of the carbon atoms are used in the formation of pi bonds. Figure 1.3a shows unhybridized p orbitals of the 4 carbon atoms of 1,3-butadiene before the formation of pi bonds. Overlap of pi orbitals of C1 with that of C2 and the p orbitals of C3 with C4. is shown in figure 1.3b. However, if the molecules is planar than the p orbitals of C2 and of the p orbitals of C3 with C4 is shown in figure 1.3b. However, if the molecules is planar then the p orbitals of C2 can also overlap the p orbitals of C3 just as it can overlap the p orbitals of C1 as depicted in figure 1.3. This means that there is an overlapping of p orbitals of C1 with the C2, C2 with the C3 and C3 with the C4 as shown in figure 1.3d. Therefore, all the 4 p orbitals can be treated as forming a pi molecular orbitals which cover all the 4 carbon atoms, figure 1.3e. In this condition, we do not have pairs of electrons mainly confined to the region between two nuclei. In other words, the bonds formed are no longer localized. Therefore, a molecular orbitals which is spread over the nuclei of more than 2 atoms is known as delocalized molecular orbitals, and the electrons present in it are termed delocalized electrons. The bonds thus formed are called delocalized bonds. Delocalized bonds may be defined as the bonds whose electrons are spread over the nuclei of more than 2 atoms. As in case of normal or localized pi molecular orbitals, delocalized molecular orbitals also consist of 2 electron clouds, one lying above the plane of atoms and the other lying below it. Figure 1.3e. Figure 1.3. A p orbitals of the 4 carbon of 1,3-butadiene before the formation of pi bonds. B overlap of p orbitals of C1 with C2 and C3 with C4. C overlap of p orbitals of C2 and C3. D overlap of p orbitals of C1 with C2, C2 with C3 and C3 with C4. A delocalized pi molecular orbitals of 1,3-butadiene. Effects of delocalization of bonds. The delocalization of bonds has the following effects on the system involved. Effect on the bond length. The formation of delocalized bonds cause the bond length to change from the normal value of a single, double and triple bonds. For example, the bond length between any two adjacent carbon atoms in 1,3-butadiene 149 picometer neither corresponds to carbon-carbon single bond length 154 picometer nor carbon-carbon double bond length 134 picometer. Second, effect on movement of electrons. In delocalized bonds, the electrons have a greater freedom of movements than in localized bonds. Third, effect on stability. Delocalization of bonds leads to a decrease in the energy of the system. In other words, delocalization of bonds makes the molecule more stable. This energy of stabilization is known as delocalization energy. For example, delocalization energy of 1,3-butadiene is nearly 16 kilojoule per mole. Kinds of molecules which contain delocalized bonds. Delocalizations of bonds is exhibited by 3 main kinds of structures. First, double or triple bonds in conjugations. Apart from 1,3-butadiene discussed above, benzene is another important example of molecules containing multiple bonds in conjugation, which exhibits delocalization as given below. All the carbon atoms of benzene rings are in a state of sp2 hybridization. The 3 hybridized orbitals of each carbons are involved in the formation of a 3 sigma bond, 2 with adjacent carbon atoms and 1 with hydrogen. sp2 hybridized carbon each forming 3 sigma bonds. As far as the unhybridized p orbitals of each carbon atoms is concerned, it can overlap to a small but equal extent to unhybridized p orbitals of both the adjacent carbon atoms. Possibility of overlap of p orbitals in both directions. Thus, the odd electrons in the unhybridized orbitals of each of the six carbon atoms can form pi electron clouds involving more than two atoms. In other words, the pi electrons are spread over or extensively delocalized, and this results in the formation of a molecular orbitals embracing all the six carbon atoms. The net result of this delocalization is that there are two continuous rings like electron clouds, one lying above and the other below the plane of atoms as shown below. Figure 1.4 delocalized bonds in benzene. Second, double or triple bonds in conjugation with the p orbitals on an adjacent atoms. The presence of p orbitals which may have two, one, or no electrons on an atom adjacent to a multiple bonds also leads to the formation of delocalized bonds. For example, in vinyl chloride CH2 double bond CH single bond Cl. The p orbitals of chlorine atoms having a lone pair of electrons overlap with the carbon-carbon double bond to cause delocalization as shown in the figure on the right hand side. Allylic carbanion CH2 double bond CH single bond CH2 minus affords another example of a structure exhibiting the delocalization in which p orbitals on adjacent atoms to multiple bond contains two electrons. Structures in which the p orbitals on adjacent atoms contains only one electrons are found in free radical, which while the structures in which the p orbitals does not contain any electrons are come across in carbocations. Third, hyperconjugation. This type of delocalization involves CH sigma bond adjacent to multiple bonds and is discussed later in section 1.8. 1.5 van der Waals interactions, intermolecular forces. Intermolecular forces are the attractive forces which operate between molecules of the same or different substance. These forces can be divided into different types depending upon the nature of the molecules. For instance, in covalent compounds containing polar bonds, partial negative and positive charges are produced on atoms by unequal sharing of electron pairs. As a result, majority of these molecules possesses a dipole moment. In such cases, the negative ends of one molecule which naturally attract the positive end of another molecules to give rise to intermolecular forces known as dipole-dipole interactions. However, non-polar molecules also have weak intermolecular forces as discussed below. Non-polar molecule substances such as oxygen, nitrogen, chlorine, and methane exist in the gaseous states in the form of individual covalently bonded molecules, but even such substances as well as the noble gases undergoes condensations at a lower temperature to liquid and solid states, which is accompanied by decrease of energy. This leads to the suggestion by van der Waals, a Dutch physicist, that there must be some weak intermolecular interaction between such molecules which became relatively stronger in the liquid or solid state. Subsequently, these forces came to be termed as van der Waals forces of attractions. They may be defined as the very weak forces of attraction between non-polar molecules which arises from the movement of electrons in atoms and molecules. That these forces are quite weak if is evident from the fact that non-polar molecule substance and noble gases have very low boiling point. This can be possible only if the intermolecular forces are weak and are overcome by supplying very small amount of energy. 1.5.1 Origin of van der Waals forces. To understand the origin of these forces, let us discuss two helium atoms very close together. Ordinarily, in each atom, the charges of the electrons is symmetrically distributed around its nucleus. However, since the electrons move about freely, we can imagine that at a particular instant of time, millionth of a second, the electron distribution in atom 1 becomes somewhat unsymmetrically with a slight increase in electron density on one side. Therefore, for a small fraction of a second, this atom has one and very slightly negative relative to the other end. This temporary separation of positive and negative charges produced an temporary dipole. Ordinarily, the negative charge of the electrons is distributed symmetrically. For a very short period, the electronic charges is separated more on one side of the other than the other. This produces a temporary dipole. The origin of temporary dipole. Dipole already present 1. This dipole is induced by first dipole second. The dipole on one atom can induce a dipole on a neighboring atom. The temporary dipole in turn influences the electron distribution of another atom present in its neighborhood because the negative ends of atom first repels the electrons of atom second. As a result, there is a instantaneous induced dipole in the neighboring atom. Although this picture persists for an extremely short time and the momentary and induced dipole are constantly changing, the net result is a force of attraction between the neighboring atoms. Similarly, in case of nonpolar molecules such as methane and carbotetrachloride, the average distribution of charge about the molecule is symmetrical and there is no net dipole moment. However, the instantaneous increase or decrease in the electron density in a particular region creates very short-lived temporary dipoles in portions of the molecules. This dipole induced positively oriented dipoles in neighboring molecules so as to result in a net attraction between different molecules. The forces of attraction between non-polar molecules due to temporary dipole-induced dipole interaction constitute van der Waals interactions. These are also known as London forces or dispersion forces. 1.5.2 Factors influencing van der Waals forces. As already remarked, the van der Waals forces are very weak and effective over extreme small distance. The actual magnitude of these forces depends mainly upon the following factors. First, number of electrons in a molecule. The magnitude of van der Waals forces depends upon the number of electrons in an atom on a molecule. With the increase in the number of electrons, there are some chance for the electron distribution to become unsymmetrical. As a result, the magnitude of van der Waals forces increases. Second, size of molecules. As the molecule size increases, the surface area becomes large. Consequently, the chances of unsymmetrical electron distribution increase and the van der Waals forces become stronger. Since the increase in molecular size generally runs parallel to the increase in molecular weight for the same type of substance, therefore the van der Waals forces also become relatively strong with the increase in molecular weight. That is why the boiling point of a series of similar compounds generally increase as the molecular weight increases. For instance, the boiling points of alkane increase gradually from methane CH4 to ethane C2H6 to propane C3H8 and so on. Third, molecular shapes. The magnitude of van der Waals forces also depends upon the shape of molecules. To illustrate this statement, let us consider the case of N-pentane and neopentane. N-pentane is a straight chain molecule having a large surface area, while neopentane is a compact molecule having much lesser surface area. CH3, CH2, 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 CH3 and pentane. Largest surface area, greater magnitude of van der Waals forces. CH3C, CH3 and 2CH3 groups on C. Neopentane. Lesser surface area, lesser magnitude of van der Waals forces. Due to greater surface area of N-pentane, there are more chances for the molecules of this compound to interact with each other. As a result, the magnitude of van der Waals forces is large. On the other hand, the chances of molecular interactions are much less in neopentane due to the compact shape of the molecules. Hence, the magnitude of the van der Waals forces is very small. That is why neopentane has a much lesser boiling point, 283 Kelvin, than N-pentane, 309 Kelvin. For the temperature and pressure, it may also be noted that for the same substance, the van der Waals forces are relatively stronger at lower temperature and high pressure. At low temperature, the random movement of the molecules decreases, which provides greater opportunity for the molecule interaction naturally. Therefore, the van der Waals forces are relatively stronger. At high temperature, at high pressure, the molecules get closer so that there is a strong interaction between neighboring molecules, and therefore the van der Waals forces are also stronger. Type of van der Waals interactions. It may be pointed out that apart from intermolecular forces between non-polar molecules due to temporary dipole-induced dipole interaction, the term van der Waals interaction also includes the following two types of attractive forces. First, dipole-dipole attraction. As already stated, these are forces of attraction which operate between molecules which are permanently polar in nature, such as HCl, NH3, SO2, and acetone. Second, dipole-induced dipole attraction. These forces operate between molecules, one of which is polar and the other is non-polar. Under the influence of polar molecules, a temporary dipole is induced in the non-polar molecules. This gives rise to dipole-induced dipole kind of attraction. For example, there is a weak interaction of these types between water molecules and xenon gas, due to which xenon is sparklingly soluble in water. 1.5.3 Van der Waals repulsions. The magnitude of van der Waals forces of attraction increases as the distance between the non-bonded atoms or molecules decreases. The attraction becomes maximum when the distance between the non-bonded atoms or molecules reaches a certain minimum value. This minimum distance at which the forces of attraction is maximum is equal to the sum of van der Waals radii of the non-bonded atoms or molecules. If non-bonded atoms come so closer to each other that the distance between them is lesser than the sum of their van der Waals radii, that attractive interactions turn into repulsive interactions. For example, in the Bott conformation of cyclohexane, there is a repulsive interaction between two flagpole hydrogens. This is because the distance between them is 183 picometer, while is lesser than the sum of their van der Waals radii 250 picometer. Please refer to Bott conformation of cyclohexane, Sec 3.25. 1.6 Resonance. 1.6 Resonance. It has already been studied in earlier classes that the concept of resonance or mesomers was put forward to explain the structure of compounds such as benzene. It has been suggested that if a molecule can be assigned two or more conventional valence bond structures, each of which can explain most but not all the observed properties of the compounds, the actual structure lies somewhere in between the various possible convention structures. The various possible structures are called contributing or canonical structures, and the actual structures is called a resonance hybrid. The resonance hybrid is indicated by putting a double-headed arrow between the contributing structures. The concept of hybridization of two or more conventional valence bond structures to arrive at an entirely new and individual structures, while however cannot be depicted on paper in terms of a conventional formula, in terms as resonance. One of most well-known examples of the applications of resonance is afforded by benzene. Since benzene could not be assigned any satisfactory valence bond structures which could explain all its properties, it was proposed that benzene is a resonance hybrid of structure 1 and 2. This implies that the structure of benzene is represented neither by one or nor second, but lies somewhere in between the two. It is evident that in the resonance hybrid, the bonds which link the carbon atoms neither correspond to single nor double bonds. On the other hand, all the bonds are equivalent and are intermediate between single and double bonds. This has been conferred by X-ray diffraction studies which shows that all the carbon-carbon bonds in benzene are of actual the same length, 1.397 angstrom or 139.7 picometer, which is in between that of the carbon-carbon single bond 1.54 angstrom or 154 picometer, and carbon-carbon double bond length 1.34 angstrom or 134 picometer. The resonance hybrid structures of benzene has 1.151 kilojoule per mole of energy, less than either of the contributing structures. This represents the resonance energy of the molecules. It is that energy which is responsible for the unusual stability and remarkable behavior of benzene. Note: the concept of resonance does not means that any one molecule of benzene spends a part of its time in structure 1 and the rest of time in structure 2. It also does not means that some molecules of benzene has got structure 1 and the other has got structure 2. What resonance means is that any one molecule of benzene always has the same single structure which is identical with that of any other molecules and is intermediate between structure 1 and 2. Other examples of resonance: first, carbon dioxide. Carbon dioxide is considered to be a resonance hybrid of three contributing structures as shown below: oxygen double bond carbon double bond oxygen. The next, oxygen negative single bond carbon triple bond oxygen positive. Next, oxygen positive triple bond carbon single bond oxygen negative. The observed bond length of carbon oxygen bonds in carbon dioxide 115 picometer is lesser than that of carbon oxygen double bond 122 picometer, which can be justified in terms of its resonance hybrid structures. Second, carboxylic acid. The acidic character of carboxylic acid is explained by treating the carboxylic acid as the resonance hybrid of the following contributing structures: RC OOH, RC single bond oxygen negative, double bond oxygen positive hydrogen. Third, 1,3-butadiene, 1,3-butadiene and the other conjugate dienes also exist as resonance hybrid. For example, 1,3-butadiene is a resonance hybrid of three contributing structures: CH2 negative single bond CH double bond CH single bond CH2 positive. The next, CH2 double bond CH single bond CH double bond CH2. Third, CH2 positive single bond CH double bond CH single bond CH2 negative. Use of curved arrows to show interconversion of contributing structures. Since contributing structures differ from each other only in the position of electrons, curved arrows are often used to show the flow of electrons in the conversion of one structure into another. This makes it easier to draw the various contributing structures of a given species. For example, the contributing structures of carboxylic acid may be drawn as shown below. Similarly, the contributing structures of 1,3-butadiene may be drawn as follows. 1.6.1 Conditions for resonance. According to the general theory of resonance, the various conventional structure formula contributing to the structure of resonance hybrid must satisfy the following conditions. First, the various contributing structures should differ from each other only in the position of pi electrons and lone pair of electrons, whereas the relatively arrangement of atoms or atomic nuclei to more precise and their state of hybridization must be same. Note, it may be recalled that existence of structures having the same molecular formula but different relatively arrangements of atomic nuclei leads to the phenomena of isomerism. Second, the atoms involved must lie in the same or nearly the same plane. Third, the number of pairs and unpaired electrons in each contributing structure must be the same. For example, CH2 single bond CH double bond CH single bond CH2 is not a valid contributing structures for butadiene CH2 double bond CH single bond CH double bond CH2 since it has more unpaired electrons than other contributing structures. Fourth, all the contributing structures must show the correct number of valence electrons for the element of second period. No contributing structure should have more than 8 electrons in the valence shell of the elements. For example, CH2 single bond CH double bond NH3 cannot be considered as a contributing structure since in its nitrogen has 10 electrons in the valence shell, which is not possible. Fifth, all the contributing structures should have the same or nearly the same amount of energy and the stability. Sixth, when the contributing structures differ in energy contents or relatively stability, the more stability structure makes greater contributing towards the resonance hybrid. 7. In determining the relatively stabilities of contributing structures, the following points may be noted. First, the larger the number of covalent bonds in a structure, the greater the stability. For example, CH2 double bond CH single bond CH double bond CH2 more stable. CH2 positive single bond CH double bond CH single bond CH2 negative less stable. Second, the structure involving separation of positive and negative charges are less stable than those which do not involve any separation of charge. More stable, less stable. Third, when atoms of different electronegatives are involved, the structures having negative charge on more electronegative atom and positive charge on less electronegative atom are relatively more stable than the other way round. For example, R C double bond O is more stable and uh, R C negative R single bond O positive is less stable. Fourth, the structures having like charges on adjacent atoms are unstable. Most stable, highly stable. Eighth, the more the number of contributing structures, the more stable is the resonance hybrid. 1.6.2 Properties of resonance hybrid. For stability, a resonance hybrid is always more stable than any of the contributing structures. The extent of greater stability of the resonance hybrid depends upon the number of contributing structures and their relatively stabilities. Second, resonance energy. It is a measure of stabilizations due to resonance and may be given as the difference in energy between the energies of the resonance hybrid and its most stable contributing structures. Greater the resonance energy, greater is the stability of resonance hybrid. For example, the resonance energy of benzene is about 151 kilojoule per mole. The value of resonance energy can be determined from the data involving heat of hydrogenation and heat of combustion, etc. Third, bond length. In a resonance hybrid, the bond length are different from those in the contributing structures. For instance, the carbon oxygen bond length in carbon dioxide is 1.15 angstrom or 115 picometer, as against the value of 1.22 angstrom or 122 picometer for a carbon oxygen bond double bond length. It may be seen that the concept of resonance hybridization is essentially equivalent to the delocalization of electrons. It is this delocalization of electrons which leads to the formation of stronger bonds and more stable molecules. Therefore, the term delocalization energy is often used in place of resonance energy. 1.7 Resonance effect. It is a process of permanent displacement of electrons in a molecule brought about by resonance or mesomers, generally designated as R1M effect. Unlike inductive effect, resonance or mesomers effect is transmitted through pi electrons and operate in unsaturated system, particularly those containing a suitable atoms or group in conjugation with unsaturated system. For this reason, it is also termed as conjugative effect. Star, a given atom or group is said to be in conjugation with the unsaturated system if it is directly linked to one of the atom of the multiple bonds through a single bond. For example, in case of stated below, the group G is in conjugation with carbon-carbon double bond, carbon double bond, carbon single bond G. What happens is that a resonance effect causes a delocalization of electrons and give rise to addition contributing structures due to withdrawal or release of electrons by the given group. For example, in the molecule CH2 double bond CH single bond CH double bond O, which contains carbon double bond group in a conjugation with carbon double bond carbon. Electron withdrawal by carbon double bond oxygen group cause delocalization of electrons and give rise to an additional structure as shown below. CH2 double bond CH single bond CH double bond oxygen. Next, CH2 positive CH double bond CH single bond oxygen negative. 1.7.1 Types of groups involved in resonance and their resonance effect. First, groups having electron withdrawing resonance effect minus R or minus M effect. Groups such as NO2 C double bond O C triple bond N SO3H and COOR withdraw electrons from an unsaturated linkage through resonance and are said to have minus M or minus R effect. For example, CH2 double bond CH single bond CH double bond oxygen acrolein CH2 positive CH double bond CH single bond oxygen negative minus R effect of C double bond O. Second, groups having electron releasing resonance effect plus R or plus M effect. Groups such as OH, OR, NH2, NHR, NHR, NR2, which can release electrons through resonance, are said to have a plus M or plus R effect. These groups have one or more lone pair of electrons which they furnish for conjugation with the unsaturated system. For example, CH2 double bond CH single bond Cl, vinyl chloride, CH2 negative single bond CH double bond Cl plus positive plus R effect of chlorine. It is important to remember that unlike inductive effect, resonance effect suffers practically no decrease in intensity with the increase in distance along the chain of atom. 1.7.2 Applications of resonance effect. Resonance effect is very useful in explaining the stability, ease of formation and reactivity of many chemical species as illustrated below. First, low reactivity of vinyl halides and aryl halides as compared to alkyl halides. Vinyl halides exhibit very low reactivity in nucleophilic substitution reaction. This is because the halogen atoms in vinyl halide cause delocalization of electrons due to plus R effect and gives rise to an additional contributing structures as shown below. CH2 double bond CH single bond Br gives CH2 negative CH double bond Br positive. Due to resonance stabilization, the halogen atoms gets more firmly attached to the carbon and it's not displaced readily. Similarly, low reactivity of aryl halides toward nucleophilic substitution can be explained in terms of resonance stabilization. Uh, the second, acidity of carboxylic acid. The acidic nature of carboxylic acid is due to their ionization in aqueous solution to form carboxylate ion and hydronium ion. The carboxylate ion is stabilized by resonance due to minus R effect of carbon double bond oxygen group. This makes the formation of this ion easily possible and is mainly responsible for the acidity of carboxylic acid. RCOOH plus H2O gives carboxylate ion plus hydronium ion. Even in undissociated carboxylic acid, resonance is possible, but this involves separation of charges. As such, it is much less effective than in carboxylate ion, where the resonance forms are identical. Therefore, carboxylate ion is stabilized by resonance due to a greater extent than carboxylic acids, which explain the tendency of carboxylic acids to undergo ionization. We will encounter many more examples of resonance effect in explaining the ease of formation, relative stability, and relative reactivities of many species during the course of our study. 1.8 Hyperconjugation or no bond resonance. The concept of hyperconjugation was put forth by Baker and Nathan in 1935 as a result of certain observations concerning the inductive effect of alkyl groups attached to an unsaturated system such as double bond or benzene ring. As alkyl group has electron releasing inductive effect plus I effect and order of plus I effect of different alkyl groups is CH3 trip, bracket 3 C is CH3 twice CH, CH3, CH2, CH3. But when an alkyl halide is attached to an unsaturated system such as double bond or a benzene ring, the above order of inductive effects get reversed. To account for these observations, Baker and Nathan put forward the concept of hyperconjugation, also referred to as Baker-Nathan effect. Hyperconjugation is another kind of resonance or delocalization of electrons which takes place through overlap between p orbitals or an pi orbitals and a sigma orbital of an adjacent carbon hydrogen bond. Please see footnotes. For instance, let us consider the delocalization of electrons in the alkenes. CH double bond CH2, where CH represents an alkyl group attached to carbon double bond carbon. The delocalization here may be shown as: a pi orbital is a molecular orbital which contains a pair of electrons involved in the formation of sigma bond. The pairs of electrons is known as sigma electrons. Similarly, we have pi orbitals and pi electrons. It is clear that the delocalization involves overlapping between sigma orbitals of the CH bond of allyl group and the pi orbitals of carbon-carbon double bond. As a result of this overlapping, each of the delocalized electrons is involved in binding together not merely two atoms, but it helps in binding together all the four atoms to some extent. In terms of resonance, the above situation may be taken to mean that the given alkene is a resonance hybrid of canonical form such as 1 and 2. It may be seen that hydrogen is not forming any real bond in structure 2. Therefore, the hyperconjugation is sometimes called no bond resonance. It is important to remember, however, that in actual practice, hydrogen is not free to leave its original position because structure second is highly unstable and makes only minor contribution to resonance hybrid, which resembles structure 1 very closely. Whether we look at hyperconjugation in terms of orbital overlap or resonance, what happens is that there is interaction between sigma electrons of CH bond and pi electrons of adjoining C double bond C bond C2C3 bond has some double bond character while C1 and C2 bond have some single bond character. These conclusions are supported by the experimental determination of various bond lengths in propene and other alkenes. It may be recalled that normally resonance delocalization of electrons involve pi electrons of two or more conjugated double bonds or pi electrons of one double bond and p electrons of an adjacent atoms containing non-bonding electrons. Explanation of observed order of inductive effect of alkyl group when attached to benzene ring or any other unsaturated system such as CH double bond CH2. It has been stated above that the usual electron releasing inductive effect of alkyl group follows the order CH3 thrice C, CH3 twice CH, CH3 CH2 CH3. This is the order. But when attached to benzene ring or any other unsaturated system, the order of inductive effects become CH3 CH3 CH2 CH3 twice CH, CH3 thrice C. This may be understood as follows. When a methyl group is attached to an unsaturated system as in propene CH3 CH double bond CH2, the various hyperconjugative structures possible are CH3 CH double bond CH2, then CH2 double bond CH single bond CH2 negative, H positive, CH2 double bond CH CH2 minus, H positive CH2 double bond CH single bond CH2 minus. On the other hand, when an ethyl group is attached to an unsaturated system as in 1-butene CH3 CH2 CH double bond CH2, the number of hyperconjugative structures possible is lesser as shown below. CH3 CH2 CH double bond CH2 CH3 CH double bond CH CH2 minus H positive, CH3 CH double bond CH single bond CH2 negative plus H positive. This is because the number of hyperconjugative structures possible depends upon the number of alpha hydrogen atoms, that is hydrogen attached to carbon called alpha carbon, which is directly linked to unsaturated system, since only this hydrogen participate in hyperconjugation. Now ethyl group has only two alpha hydrogens, whereas methyl group has three such hydrogens. Similarly, the number of hyperconjugative structures possible for CH3 twice CH will be still lesser, and no such structure will be possible for CH3 thrice C. As the number of possible hyperconjugative structures goes on decreasing, the electron releasing tendency of alkyl group goes on decreasing. In hyperconjugation in neutral molecules such as alkenes, the hyperconjugation form displays not only no bond resonance but also charge separation not shown by the main form. This can be easily seen from the examples of propene and 1-butene shown above. This kind of hyperconjugation is called sacrificial hyperconjugation. In case of free radicals and carbocations discussed in Sec 2.5 and 2.7, the hyperconjugative forms involves only no bond resonance but no charge separation not shown by the main form. This is known as isovalent hyperconjugation. Application of hyperconjugation. The concept of hyperconjugation is widely used in the study of organic chemistry. For example, first, it helps to explain the relative stability of alkene. Please refer to chapter on alkenes. Second, it is used to explain the relative stability of carbocation and free radicals. Please refer to chapter 2. 1.9 Inductive effect. The concept of inductive effect concerns the shift of electrical charges within a molecule arises out of the presence of a polar covalent bond in the molecules. To illustrate this, let us consider a molecule having a chain of carbon atoms with the chlorine atoms linked to the end carbon atoms such as C4, C3, C2, C1, Cl. Due to greater electronegativity of chlorine, the electron pairs of the bond between C1 and Cl is displaced towards a chlorine atom. As a result, polarization of the bond takes place. Chlorine acquires a small negative charge while C1 becomes slightly positive charge as shown below. C4, C3, C2, C1 slightly positive, Cl slightly negative. Now the positive charge C1 exerts an attractive influence upon the electron pair shared between C1 and C2. Due to the resultant electron displacement towards C1, the positive charge on C1 is partially neutralized when a small positive charge develops on C2, but the charge on C2 is smaller than that of C1. The positively charged C2 in turn attracts the electron pair of the bond between itself and C3, thereby making C3 also very slightly positive charged. This process of electron shift along the chain of atoms due to the presence of polar covalent bond in a molecule is known as inductive effect. It is represented by an arrow as shown below: C4, C3, C2, C1, Cl. Inductive effect is sometimes also called a transmission effect because it is transmitted through the bonds constituting the chain of atoms. It should be noted that the effect along the chain of atoms is not the same throughout. It decreases sharply as we move away from the initial polar bonds and is negligible from fourth atom upwards. It must also be understood that inductive effect does not involve any actual transfer of electrons from one atom to the other. It merely helps in displacing them permanently. 1.9.1 Types of inductive effect. Inductive effect is a relatively effect and may involve attraction of electrons towards a group of or repulsion of electrons away from it. For comparing the relative inductive effect of various groups, hydrogen is commonly taken as the standard, and accordingly groups are divided into two categories. First, electron withdrawing or attracting inductive effect denotes as -I effect. Atoms or groups which have a greater electron attracting capacity than hydrogen are said to have -I effect. The decreasing order of -I effect of some common groups is as follows: Nr3, Sr2, NH3, NO2, SO3H, Cn, COH, FCl, Bri, OC6H5, COOR, OROH, C6H5 -I effect decreasing order. It may be noted that comparing two hydrogens, most groups are electro-withdrawing. Second, electron releasing or repelling inductive effect, denoted as +I effect. Atoms or groups which have lesser electron attracting capacity than hydrogen are said to have a +I effect. The most important electron releasing group are alkyl groups. At the same time, many groups having a formal negative charge and atoms of lower electronegativity such as Si, Mg, and Li are electron releasing. The decreasing order of some groups having a +I effect is as follows: O negative, COO negative, CH3 thrice C, CH3 twice CH, CH3, CH2, CH3D. +I effect decreasing order. It may be noted that in case of alkyl groups, the more highly substituted the alkyl groups, the greater is its +I effect. 1.9.2 Applications of inductive effect. Inductive effect plays a very important role in organic chemistry, as illustrated below. First, comparison of relative acidic strength of organic acids. In aqueous solution, a carboxylic acid exists in equilibrium with the carboxylate ion and hydronium ion, that is RCOOH plus H2O, equilibrium with RCOO negative plus hydronium ion, H3O positive. The strength of the acid is generally expressed in terms of equilibrium constant Ka, known as acidity constant, which is given by the expression Ka is equal to RCOO negative H3O positive divided by RCOOH. Since K is directly proportional to the concentration of H3O positive ions, it would have a low value in case of weak acids and a high value for strong acids. The position of the equilibrium in the reaction between a carboxylic acid and a water to furnish carboxylate ion and the hydronium ion depends upon the stability of the products relative to the stability of the reactants. RCOOH plus H2O in equilibrium with RCOOH negative plus H3O positive. Any factor which stabilizes the carboxylate ion more than the parent acid should increase the acidity, and any factor which destabilizes the ion should decrease the acidity. A group having electron withdrawing inductive effect, say G, on the carboxylate ion attracts electron towards itself and thus disperses the negative charge of the ion. As a result, its stability stabilizes the carboxylate ion and thus increase the acidity of the parent acid. GCH2 COO negative, GCH2COO negative. G disperses negative charge by withdrawing electrons, stabilize carboxylate ion, increases acidic character. G dash intensify negative charge by releasing electrons, destabilize carboxylate ion, decreases acidic strength. A group having electron releasing inductive effect, say Z dash, on the carboxylate ion intensify the negative charge of the ion and thereby destabilize the ion. Consequently, it decreases the acidity of the parent acid. In short, it may be stated that the electron withdrawing group increases the acidity while electron releasing group decreases the acidity of carboxylic acid. Let us for instance compare the acidity of acetic acid and chloroacetic acid. It is found that chloroacetic acid is about 80 times stronger than acetic acid. It is due to the fact that in acetic acid the electron releasing inductive effect of methyl group destabilizes the carboxylate ion. On the other hand, the chlorine present in the chloroacetic acid exerts an electron withdrawing inductive effect and thus stabilizes the carboxylate ion by dispersing its negative charge. CH3COOH equilibrium CH3COO negative plus hydronium and H3O positive. CH3 group has electron releasing effect and tends to intensify the negative charge on oxygen. ClCH2COOH equilibrium ClCH2 COO negative plus H3O positive. Chlorine has electron withdrawing effect and tends to disperse the negative charge on oxygen. Similarly, it can be explained by why acetic acid is weaker than even formic acid. Acetic acid contains the CH3 group having electron releasing inductive effect attached to the carboxylic group, which destabilize the carboxylate ion by intensification of charge. On the other hand, formic acid has only a hydrogen which has no destabilizing effect on the carboxylate ion. Second, comparison of relative basicities of amines. Like ammonia, all amines are basic in nature. A convenient way of expressing the basic strength of amines in its term of equilibrium constant Kb, known as basicity constant, which is derived from the following equilibrium. R NH2 plus water, equilibrium R positive NH3 plus OH negative. Kb is equal to R positive NH3 OH negative divided by R NH2. The greater the value of Kb, the greater is the basicity of amines. The basicity of amines depends upon the availability of electron pairs on nitrogen atoms and the stability of the substituted ammonium ions formed. Any factor that increases the availability of electron pair on nitrogen or increase the stability of ammonium ion relative to the parent amine while increase the basicity of amine. On the other hand, any factor that has the opposite effect which decreases the basicity. It has been found that aliphatic amines have greater basicity than ammonia. It can be explained in terms of the electron releasing inductive effect of alkyl group. Aliphatic amines contains one or more alkyl group in place of hydrogen atoms of ammonia. Now an alkyl group being electron releasing increases the electron density on nitrogen and thus makes the electron pair on nitrogen more available for sharing. At the same time, the electron releasing inductive effect of alkyl group decreases the positive charge of the substituted ammonium ion formed by the amine and thus increases the stability. RNH2 plus H positive. R helps to increase the electron density around nitrogen and makes the electron pair more available. RNH3 positive. R disperses the positive charge of the ion and thus increases the stability. It may be noted that due to inductive effect alone, a tertiary amine should be more basic than secondary amine, which in turn should be more basic than a primary amine. But the actual order is not found to be same always. This is because relative basicities of primary, secondary and tertiary amines cannot be explained in terms of inductive effect alone. There are other factors also which plays their role. This is discussed in detail at a later stage. Third, comparison of basic strength of ethylamine and acetamide. Ethylamine is much stronger base than acetamide. This is because the plus R effect of ethyl group of ethylamine increases the electron density on nitrogen, which gets easily protonated. C2H5 NH2 plus I effect of C2H5 high electron density on nitrogen. CH3 C double bond O NH2 CH3C single bond oxygen negative double bond NH2 positive reduce electron density on nitrogen due to resonance. On the other hand, the electron pair on nitrogen of acetamide gets delocalized due to resonance as shown above. As a result, electron density on nitrogen decreases and its basic character gets suppressed. Fourth, comparison of relative stability of species as carbocations and carbanions. Please refer to chapter 3. 5. Cause of relativity of many compounds. Inductive effect helps us in understanding the cause of reactivity of many compounds as discussed at appropriate places in the text. 1.9.3 Comparison of resonance and inductive effect. Resonance effects operates in unsaturated system, particularly in conjugated system through the pi electrons. Inductive effect. It operates even in saturated systems. Presence of unsaturation is not a necessary condition. Resonance effect. Second, it involves a displacement of non-bonding and pi electrons. Inductive effect. It involves a displacement of sigma electrons. Resonance effect. During the resonance, electron pair is completely transferred, leading to the development of fully positive and negative charges. Inductive effect. The electron pairs is only slightly displaced from its position so that only partial positive and negative charges appear. Resonance effect. It leads to delocalization of electrons. Inductive effect. No delocalization of electrons takes place. Fourth, resonance effect. It is transmitted over large distance without undergoing any change in intensity. Inductive effect. It decreases sharply with the increase in distance and operates only very over short distances. 1.10 Electromeric effect. Electromeric effect is a temporary phenomena which operates during some reactions involving molecules containing double or triple bonds. It consists of an instantaneous and complete transfer of a shared pair of electrons of the multiple bond to one of the bonded atoms due to the requirements of some attacking reagents. Electromeric effect is usually denoted as E effect, and the transfer of electrons take place is represented by a curve arrow as shown below. A double bond B attacking reagent, A positive, single bond B negative. Since A loses its share in the electron pair to B, A acquires a positive charge and B gets a negative charge. This structure is evidently not so stable as the normal structure and is formed only at a moment of reaction under the requirement of attacking reagent. If the attacking reagent is withdrawn without the reaction being allowed to take place, electron distribution reverts to its normal state. In other words, the electromeric effect involves temporary polarization at the seat of multiple bonds. An electromeric shifting of electrons proceed most reactions involving addition to multiple bonds. Let us, for instance, consider a molecule containing a carbonyl group C double bond O. When a reagent such as Cn negative ions attacks the carbonyl group, one of the shared pair of electrons, the pair constituting the pi bond, is transferred to oxygen. As a result, the carbon atom becomes positively charged while oxygen acquires negative charge, and the attacking reagent immediately forms a bond with the positive charge carbon as depicted below. C double bond O plus Cn negative gives CnO negative. It is quite obvious that the electron pairs cannot be transferred to the carbon atoms because oxygen is more electronegative as compared with carbon. 1.10.1 Types of electromeric effect. Electromeric effect can also be divided into two types as explained below. First, plus E effect. When the pi electrons are transferred to the atoms of the multiple bonds which get bonded to the attacking reagent, electromeric effect is known as plus E effect. For example, C double bond C plus H positive gives C positive CH. Second, minus E effect. When the pi electrons are transferred away from the atoms of a multiple bond which gets bonded to the attacking reagent, electromeric effect is known as minus E effect. For example, C double bond O plus Cn negative gives CnO negative. 1.10.2 Significance of electromeric effect. Electromeric effect is very helpful in explaining the mechanism of addition reaction of organic compounds containing the multiple bonds. As we we will be seen at different places in the text. If both inductive and isomeric effects operate together, this may assist or oppose each other. In case they are opposed to each other, the electromagnetic effect generally overcomes the inductive effect. Comparison of inductive effect and electromagnetic effect. Conductive effect. It is temporary effect which involves a mere displacement of electrons. There is only a distortion in the shape of molecular orbitals containing the displaced electrons. The electrons do not leave the molecular orbitals. Electromagnetic effect. It is a temporary effect which involves the cleavage of a multiple bond and the complete transfer of shared electron pairs to one of the atoms. The electron pairs of the multiple bonds leaves its molecular orbitals completely and is transferred to one of the atoms. Inductive effect. The only requirement for this effect to operate is the presence of some polar bonds in a molecule. It is not necessary for the molecules to contain a multiple bond. It does not require an outside attacking reagent. It involves a partial separation of charge. Electromagnetic effect. It can be exhibited only by molecules containing at least one multiple bonds which may or may not be polar in nature. It can take place only under the influence of an attacking reagent. It involves a complete separation of charge. Thank you.